Our final lesson for Unit 7 is the applications of vectors in terms of dot and cross product. So what sorts of things do these operations correspond to in the physical world and in other virtual worlds? The first thing to try to get your head around is the concept of a projection. Now, a projection is not overly difficult to do, but it is a little bit difficult to understand. I try to think of a projection as in a sense of like how if one vector were to cast a shadow onto another vector, right? What would that shadow be? So like you try and think about it like you're standing up straight, but your shadow is being cast onto the ground, or it's being cast onto a wall, or it's being cast onto some surface. Now your shadow, right, has to be like it has to be on that surface. It has to either be on that wall or be on that bench or be on that ground, and therefore it has to be, going in the same direction as that other object. So if you this picture here does a nice job of it. You have vector A and you have vector B, and then you have this section in the dark or the red section down here. This is the projection that vector A casts on vector B. Another way of thinking about it is like if you were to divide A into two components, one component in the direction of B and one component perpendicular to B, the projection would be which component is the one that's parallel with B. Let me just visually draw a couple more of these for you so you can see. So here, okay, so again, this is a similar one to the one in the book. Vector V is pointed off and to the side. Vector U is pointed straight to the right. And you can see the projection is just, it's like if V were the sum of a right vector and an up vector, it would just be the right part. Now, if U were pointed in a different direction, right? Now we're asking, like, how far in the direction of U does V actually go? And you can see it does not go very far here. Most of V's movement is perpendicular or in the perpendicular component to U. And actually, if we make these things actually perpendicular, so that would be, let me just make this be a bit easier. If this was 4 and this could be -3, if they're actually perpendicular, there is no projection. And this would be akin to you asking, where's my shadow? If the sun is directly on top of you, the shadow would not be left or right. It would just be directly underneath you. It would have the projection would be 0. So getting your head around visualizing this, it can be difficult, right? And first, I guess another thing I should point out is if they're going in the same direction, then the projection of V onto U is just V, because all of V is basically being used in that direction. So again, if V gets taller, let's put U back to being flat just to demonstrate something. If V gets taller or shorter, it has no effect whatsoever on the projection, right? If you change the perpendicular component. If you change the component, the left and right component, then that projection is going to be altered. There are two ways that this projection can occur, and there are two types of projection as well. There's a scalar projection and a vector projection. So let's talk about both of those. If it's the case that the angle between the two vectors is less than 90 degrees, so it's acute, then the projection of one vector onto the other will always kind of look like this. It could be rotated a bit, but it'll always ultimately have this same picture. The projection of A onto B is the vector ON. Okay, that makes sense, right? OA, OB, and then ON would be the projection. And then the different notations, but the one we use is this one. You write proj. Let me just zoom in on this so we can see it more clearly. Okay, you write proj. The vector you're projecting onto, it gets a subscript, and then the vector you're projecting is up in the main line. So if you see this, how you read this is the projection of vector A onto vector B. Now the magnitude of this is actually really simple. It would just be the magnitude of A times cos theta, because cos theta would be the adjacent in this little triangle. So it would be A cos theta. Now, cos theta, you know, could also be rewritten as A dot B over magnitude A magnitude B, because, you know, you just go back to the dot product formula for a sec. So I'm just going to say A dot B equals magnitude A magnitude B cos theta, right? Just to remind you. So if you isolate cos theta, you would send the A dot B, you send the magnitude AB underneath A dot B, and that's how they get this step. And then they just cancel a magnitude A and a magnitude A to end up with this. Now this, of course, is a scalar, because A dot B is a scalar, and then B underneath is the is a magnitude, right? So it's also a scalar. So what you would say here is you would say the scalar projection of A onto B is A dot B over B units, and then you'd say in the same direction as B. Okay? That would be its direction. Now again, if they're only asking for the scalar projection, that's what you do. You just give the number, and then you say it's in the same direction as B. Now, you can also project when the angle between them is 180, or sorry, is bigger than 90. So let's imagine we point V the other way. Okay? Now the projection is actually still parallel with U, but it is pointing in the opposite direction of U. And this will happen whenever the angle between the two vectors is greater than 90. Okay? So let's just recap this for a second. If the angle is acute, you will project in the direction of U. If the angle is 90, you will just project a 0. If the angle is obtuse, you will project in the opposite direction of U. But actually, the formula doesn't really need to change because, well, okay, let me just try to clarify this. So when you project A onto B and the angle between them is bigger than 90, what happens is you get, it's the opposite of A cos theta. Now, the reason that they're putting an opposite here, okay, is because otherwise you would get a negative magnitude, right? Because cos theta is a negative number when theta is bigger than 90. Magnitude A is a positive number. So if you multiply those two together, you get a negative. Now, of course, it's up to you how you want to handle this. If you want to remember that there's a negative in the formula, then remember that. I think it's a little bit easier to just say, if you ever project and get a negative answer, you could only have gotten that negative answer because the angle was bigger than 180, and therefore it's going in the opposite direction. Okay? So just please be careful with this, though, because you can't give the answer as a negative. You can't say the projection is -6. Okay? If you get an answer that's -6, you remember, okay, what does negative mean? Negative means I'm projecting in the opposite direction of B, but the length of that projection is not -6, it would be 6. So this negative is here to cancel the fact that A dot B is going to be a negative number because B is bigger, the theta, is bigger than 90. I don't think I would bother remembering that. I would just remember that the projection formula is the same, whether the angle is bigger or smaller than 90. And I would just remember that if my final answer is negative, what negative means is that it's pointing in the opposite direction of vector B. So this is a good picture, right? Vector B is pointed to the right, but the projection actually goes to the left. Okay? Right, so this is just saying it's in the opposite direction. So again, when you give an answer, you say the projection is 6 or the projection is 8 in the opposite direction of B, and that's your scalar projection. Now, of course, if theta is 90 degrees, then when you project A onto B, you get 0, because basically it's like saying how far in the direction of B are you moving if you move along vector A? And the answer is 0. A person standing at O versus a person standing at A, neither one of them has moved any distance at all in the direction of B. So the projection is just 0. Okay? So again, find the scalar projection. I don't think this is a particularly challenging question. It's just remembering what we know. Again, bear with me while I write out. I just want to make sure we have everything correct here in the notes. So let's write what we know. What we know is that A dot B is equal to magnitude A, magnitude B, cos theta. So that's what we know. And we also know, we also know that to project, okay, now I got to do a subscript. When I'm projecting B onto A this time. So the A goes down here, and then the B goes here. Oh my goodness. Okay. No, okay, I see what I'm doing. Okay, so you B vec. Sorry. Okay, so this time we are projecting the B. So we're projecting B onto A. So actually, I've messed this up. B onto A, right? Because that's when we're doing A, the big A, and the little b is projecting A onto B like we were doing before. This time we're projecting B onto A. Now the projection of B B onto A. I had it right the way I wrote it. Right, the lower cases in A. I'm so sorry. I wrote it right. I said it wrong. Okay, so this is what we're trying to find. Now, the formula says, so let's just go back to the formula for a second. So look at the formula. When you're projecting A onto B, it's A dot B over B. When we're projecting B onto A, it's going to be the same thing. It's going to be B dot A, which is the same as A dot B, except instead of over B, it's going to be over A. So that's all, right? So we get, I'm just going to copy paste this. A dot B over, instead of magnitude B like it was before, it's over magnitude A. Oh boy. There we go. Okay, so A dot B over A. Now, this, of course, you know, even this is a bit of overkill in this question, because if you just imagine, if you just draw this for a second, right? Let's just draw this. You think about the information that they already gave us. So whenever I draw a projection question, so it says given two vectors of A and B, the angle between them is 120. Let's just make it easy on ourselves. Let's make one vector point directly to the right, because there's no reason not to. Let's make the other vector go at 120 degrees. So we're just going to go, sorry, we'll just insert a little text box here. Okay, so this is what we know. Okay, now the projection, the thing that I'm looking for, right? It would be, you know, how far is basically that? And let's just put that in red. Okay, click red and get a very faint gray. Pause this while I fix it. Okay. I hope I didn't curse there, because I don't think I actually paused it. So here's your projection here. You can see it's not pointed in the direction of... So again, just to clarify, this down here is vector A, this is vector B. We're projecting vector B onto vector A. the answer is going to be in the opposite direction. And then just imagine this was not a vectors question for a sec, right? And what would you do? You know that this angle in here is 60 degrees, and you know that this length, right, is 16. So whatever is down here is just 16 times cos 60, right? Then that would have to be whatever gives us the answer. We can continue to do it this way if we want to, but of course if you use the formula, you're just going to end up with overkill, because look what happens when you use the formula. Oh boy. Okay. Diagrams on Microsoft Word. Is that all going to move or not going to move? No, it isn't. Okay, so anyway, sorry, the formula. What's A dot B, right? A dot B is this. Magnitude A, magnitude B, cos theta. So if we go back and put that in, right, you have magnitude A cancels magnitude A, and all you're doing here is the magnitude of B times cos theta. What's the magnitude of B? It's this length right here. Cos theta, now just to be careful, cos theta is 120. So when you do cos of 120, you get negative 0.5. But, you know, it's up to you, again, to remember, do I do it with a negative, or do I do it with, so 16 times cos 120 equals negative 8. Now, what does negative 8 mean? Because the formula, remember, the projection is never negative. So my answer would be, so as I put my answer, so the scalar projection is 8 units in the opposite direction of A. Okay, so that's what the negative 8 means there. Okay, again, it's not negative 8. You can't leave your answer as negative 8. Okay, so just try to remember that, because that's important. Okay, 2 vectors of magnitude. So again, this is a very, very simple question. It takes you 15 seconds to do it. All you do is you go, okay, the scalar projection is, is b cos theta. That's it. B cos theta is the answer. But of course, what does it mean? How do I draw it? Why is it negative? All that stuff, you got to make sure you can think through and follow. Okay? Okay, what is the scalar projection of vector u onto vector v? So again, let's write this out. So the scalar projection of vector u onto vector v, remember the onto part is under onto v, okay, is u dot v. Again, it doesn't matter which order you put those in. And then which one goes at the bottom is whatever one is in the subscript below, right? So just like up here, A is in the subscript because that's what we're projecting onto. That goes on the bottom. Over here, B is in the subscript because that's what we're projecting onto, and B goes on the bottom, right? So this is it. So we project u onto v by doing this, and we're just going to have to find the dot product. So the dot product is equal to 3 times 2, which is 6, plus 4 times negative 2, which is negative 8, and then plus 6 times 2, which is 12. So 18 take away 8, the dot product is 10. Okay, the magnitude of v, don't actually need the magnitude of u, right? But the magnitude of v, it'd be 2 squared plus 4 squared plus 2 squared, which is 24. And then we need the square root. Okay, well, I don't need brackets, but okay. The square root is, the magnitude is square root 24. So therefore, the projection, right, just fill in the numbers. Take the dot product, replace the dot product with 10. The bottom part will be square root 24. Okay, now this number, right, it's positive because these two vectors must have an acute angle between them, which we discovered when we did their dot product. So to finalize the answer, I'm just going to say it's that many units in the direction of v. Okay, so let's draw this so you can kind of see what I'm doing, and this will also help introduce the next concept which is the vector projection. Okay, so let's draw what we had. So 3, -2, 6. Okay, v is 2, 4, 2. Okay, now, first thing we should notice, the angle between them is indeed acute, right? It's not, like if you look at it as though they were on a plane, you can see that it's not bigger than 90 degrees for sure. Okay, so those are the two vectors. We're trying to project, right? We're trying to project u onto v. So let's just change the color of u here. So we'll make u blue. We're trying to ask ourselves, how far in the direction of the black vector does the u vector, does the blue vector actually travel? And what we found, right, is that the answer, so let's call it magnitude, was 10 divided by square root 24. And so what I'm going to do now is I'm going to make a unit vector in the direction of v. So what I'm going to do is I'm going to do vector v times 1 over length v, right? And what this does, just to remind you, it creates a little vector down here that's pointed in the same direction as as v, but only has magnitude 1. Now, our projection, we said, has a magnitude of 2.04. So if I take that magnitude 1 vector and scale it up by that amount, right, I get this. And let's just make this red. And let's hide the rest of it. And you can see that the red vector is the size of the shadow, right, that the blue vector casts in that direction. Right? So again, vector v is that black, but if you moved along the blue vector, you would only move this red piece towards the end, or in the direction of the black vector. Right? So that it's still the same idea of projecting a shadow. It's just projecting it onto a 3D, from one vector onto another in 3D. But the concept is still very, very similar. Okay? All right. So it's positive, so it's in the direction of u, or in the direction of v. We got that. Everything's good. The scalar projection of a onto b is 8. If the length of a is 11, then what is the angle to the nearest degree between a and b? Okay, great question, right? Because it's not super hard, but again, you need to know your stuff. Otherwise, it just seems like all this crazy information. Let's go back and look at our formula. So I'm going to go back to this one. So we are projecting a onto b. So first of all, I have this wrong, right? This is what gets projected. This is what you project onto. And of course, whatever you project onto has to be in the denominator. Okay, so there I'm projecting a onto b. What can I figure out, and what do I need? Scalar projection of a onto b is 8. Now technically it should say either in the direction or not in the direction, but we'll address that at the end of the question. Now we know the length of a is 11, and we don't know the angle to the nearest degree. So let's try and figure this out. Let's write what we know. I'm going to replace the projection with 8, because that's what it says. It says the length of a is 11. So I'm going to take a dot b on the top, and I'm going to replace a dot b with ab cos theta. Okay, I'm going to then divide this by the magnitude of b, because that's still on the bottom. Okay, so what happens here? You get 8 equals the magnitude of a times cos theta, because the two magnitude b's cancel, right? And it says the length of a is 11, so 8 over 11 is equal to cos theta. Therefore, theta is equal to 43.34, or 180 minus that number in quadrant 2. So 43.34 or 136. So let's just say 43 or 137. Now, why am I giving two answers here? I'm going to say underneath this, the question does not specify whether the scalar projection is in the direction of B. Oops. Or in the opposite direction. Therefore, the angle between the vectors is 43 degrees if the projection is in the direction of B, or 137 degrees if the projection is in the opposite direction of B. Okay? Okay? And that's just I'm just being technical here, but if I'm going to tell you that you need to make sure you say the direction, then I expect, if it doesn't say the direction, we need to address that. So since it's not clear in the question which way it's pointing, we'll just give both answers. All right, now we get into the real meat of the day, the vector projection. Now, in my opinion, if you find this overwhelming, what I would do is learn the vector projection only, and then remember that the scalar projection is just its magnitude. Okay, so let's just start with that right off the bat. So the magnitude of the vector projection is the scalar projection. Okay, so if you learn the vector projection, which is a bit of a more difficult formula, and then you just remember that to get the scale, whenever it asks you for the scalar one, just take its magnitude. That's it. Now, what is this? This is exactly what I just showed you on this picture. How did I figure out how to draw the vector in red? Okay, I did a unit vector in the direction of V, and then I scaled that unit vector by the magnitude of the scalar projection. Now that's all that this formula is. Look, A dot B over B is the scalar projection, which is telling you how long the projection has to be, and then the B over B part is just giving you the direction. It's giving you a unit vector in the direction of B. So the whole idea here, the idea behind this formula, is to find a unit vector in the direction of B and then scale it up, I guess I should say, or down, by the magnitude of the scalar projection to make sure it has the correct length. So again, how do you get a vector to have a length of 8? Find a unit vector in the direction you want and then multiply everything by 8. So that's all we're doing here. This big chunk turns into a scalar that tells you how long your vector is supposed to be. This tells you a vector of length 1 that you're simply going to scale up by this number. When you look at this, all this is doing is just collecting these two things into what might be a slightly more readable formula, but I actually not even sure I like this formula. I think I like it better like this because it reminds you where it comes from. It's the scalar projection times a unit vector. Okay? So it says find the vector projection of A and B. All right. So first of all, let's start by remembering to find a vector projection, we need to find the scalar projection and a unit vector in the direction of B. Okay, so let's do this task. So first we start with vector B divided by magnitude vector B. Okay, this is our unit vector. So remember, this is always the same formula. If you want to create a unit vector, take your vector, divide by magnitude equals unit vector. All right, let's draw it with the correct terminology. So remember, it's B hat. Okay, that's what that means. So it's a unit vector in the direction of B. And in our case, how do we solve this? We simply look for the magnitude of B, which would be the square root of, let's see, 3 squared is 9, 4 squared is 16, and 1 squared is 1, so that's 26. So the magnitude is root 26. So what does the unit vector look like? So b hat. Okay, the unit vector is simply 1 over square root 26, comma 3 over square root 26, comma 4 over square root 26. Okay, now I have a unit vector in the direction of b. Now, how far is my unit vector supposed to go? It's probably not supposed to have a magnitude of 1, because when you project A onto B, we don't know that magnitude. We need to find it. So let's go back up here and copy paste my formulas. Don't have to watch this over and over again. Okay. Which one am I projecting onto which? I'm projecting A onto B. Well, actually, this is very poorly written, right? You should never say the vector projection of A and B. That doesn't make sense. Change this to onto B. Okay, you need to know which one is projecting onto which one. So A is projecting onto B. To project A onto B, A should go here. B should go there, and whichever one's in the subscript should go in the denominator. Okay, so A dot B over magnitude B. I already know magnitude B, right? It's 26, root 26. So I just need their dot product. So again, I already know the answer on the bottom. Let's just say it's a 1 for now, just so I can. Okay, so what is A dot B now? So let's go through A dot B. Negative 3 times 1 is negative 3. Okay, 2 times 3 is 6, and 4 times 1 is 4. So what you end up with here, the projection, we know, is going to have a magnitude of 7 over square root 26. Okay, so all you had to do to answer this question is those two steps. You know how to make a unit vector. We've done this before. You know how to do a projection because we did it above. So how do you make a vector projection? You just stick these two things together. So projecting A onto B is going to be equal to this value, the 7 over root 26, as a scalar multiple times this vector. Okay, so notice what's going to happen here. The final vector, final answer, the root 26s are going to sort of they're going to multiply together and just become regular 26s, and then we just get this as a final answer. 7 over 26, 3 over 26, excuse me, 21 over 26 and 28 over 26. Okay, and this vector is the amount of B you would travel if you were traveling along vector A, or the vector of the shadow that A casts onto B. Now again, let me draw this so that you can see what it looks like. So let's just start this all over again. Okay, so we're going to begin with vector A, negative 3, 2, 1. A, negative 3, 2, 1. Okay, vector B is 1, 3, 4. Okay, and again, our question is how long. So let's change their colors here. We'll make a I guess blue, green, and red are kind of out. So let's make it purple, and we'll make B. It's kind of orange. That's grotesque. Alright, well, whatever. Okay, so if we were going to project A onto B here, right? So B, let's just make it blue so it's more straightforward. Okay, projecting A onto B, it would cast a shadow, somewhere like going up approximately to here, thereabouts, right? Let's draw the vector we created as our answer. Our answer was 7 over 26, 21 over 26. Sorry, let's make this, let's call it proj. And 28 over 26. Now look at that projection. Okay? It's perfectly in the direction of B, and it's the exact shadow, right? If you sort of get A directly behind it, it's the exact shadow that A would cast in the direction of B. Okay? So again, the concept is still the same as it is in 2 dimensions. How far along the blue vector would you move if you moved along the pink vector? Okay? And our answer is right here. The best way to remember this is to try to remember it as the scalar projection times a unit vector. If you ever needed to get the scalar projection, so the scalar projection could be determined by dividing or by finding the magnitude of this vector projection. Remember though, if the dot product was negative in your process, then the scalar projection is in the opposite direction. Okay, so I think my advice actually isn't very good. I think it's probably best to just remember the scalar projection and remember how to do a unit vector. And then whenever you need a vector projection, you just collect those two skills together. Just do them both and multiply them together, and that's your answer. I do not think I would invest in remembering this formula, although it should be clear to you that this formula is not very different from this one. Okay, now we're going to do a couple of things that are applications. So work and torque and volume and more volume. All right. Okay, now work. So we talked about work before. Of course, you should be thinking, what does work have to do with this? Work is like if I have a force V, the work I'm doing is the projection. We didn't learn projections when we did work. We just said it was VU cos theta, right? But the projection tells you the amount of force that V is actually doing in U's direction. So another way you could define work is you project V onto U. That tells you your net force, and then you simply multiply it by how much distance you're traveling. Makes it really easy. So again, the work we said was equal to F dot D. But now you kind of know that F cos theta is actually the projection of F onto D, and when you multiply that by D, you're doing the force times the distance, which is how you get work. Again, there really is nothing to this work. All you have to do is just do the dot product. So just do the dot product. That's all it takes to do the work. Okay, so let's do this first one. It says F is 200, D is 3, theta is 45. So let me just separate this so it's easier to see. So I'm going to say work done, which does not have a vector symbol above it, right? Because work is not a vector, it's a scalar. Okay, is equal to the vector, the force vector, okay, dotted with the displacement vector. Okay, so that's how you get work done. Okay, now in our case, they tell us the magnitudes and the angle, so just magnitude F, magnitude D, cos theta, and theta is 45 degrees. We know that is 1 over root 2, so we have 200 times 3 times 1 over square root 2. Okay, and so we just end up with the answer 600 over square root 2. You can rationalize it if you want. You don't have to. Work done by a force if, and so we just make sure you give a unit in your answer. Joules, or you can say Newton meters. Either one is acceptable, or just a capital J for joules is also fine. Okay, so that's it. Very simple. Same thing down here. The force is equal to, the work done is equal to the force dot the distance. So even in 3D, nothing changes here. It's just we probably don't know the angle between the two vectors in 3D. So 3, -5, and 1, that would be the force vector. The displacement vector is -1, 5, -3. And the work done is simply -3 minus 25 minus 3. The work done is negative 31. Now, of course, work, what does negative work mean? It doesn't mean negative energy or energy has been created. It just means 31 joules in the opposite direction of D. Right? So it's like, I'll draw it and you can kind of see what I mean. But it's kind of a silly question because you're kind of like pulling the thing backwards instead of forwards. But anyway, F is equal to 3, -5, 1. D is equal to -1, 5, -3. Sorry, I see. So vector. Let's call it force. Okay, so then when I go dot D with force, it gives me -31. Now, why is it giving me a negative? Well, think about it this way. If your object, was, if the displacement of the object is going in this direction, but the force is pulling in this direction, the work is actually resisting, like it's not, it's just giving you a negative to show that this force would not actually pull an object in that direction. It would pull an object in this direction, right? If this is a hill, it's pulling it up the hill rather than pushing it down. I think this is kind of silly, personally. I'm not really sure if this example is intended to be negative or not. But let's just say, in this question, the work done would be opposite. It's like the object's sliding away from you and you're pulling it in the opposite direction. I don't know. I don't know what to do with. I don't know what to make of this. But mathematically, what I'll say is, it's this many joules in the opposite direction of D. Okay. Now, it says a crate on a ramp is hauled 8 meters up the ramp under a constant force of 20 newtons applied at an angle of 30 degrees to the ramp. Find the work done. Okay, so I don't know why we've gone back to these ramp questions, but this is the exact same thing as what we did back in earlier in the unit. I think it was Unit 6 that we talked about these ramp questions. But anyway, so as a crate on a ramp is hauled 8 meters up the ramp under a constant force of 20 newtons applied at an angle of 30 degrees to the ramp. Again, don't overthink this question. The work done is equal to the force that's doing the work dot the displacement, the object's displacement. That's it. Now let's think about this. The displacement is 8 meters, right? So that's what that says. So magnitude is 8, okay? And the force is 20 newtons applied at an angle of 30 degrees to the ramp. So 30 degrees to the ramp is just telling you that theta is 30 degrees. The angle between the two vectors is 30 degrees. The magnitude of vector F, right, is equal to 20. So, I don't need a fancy diagram or a normal force or anything complicated here. All it's asking is for work done. You know the force that's doing the work, and you know the displacement that the object underwent. So all we're going to do is just do the dot product, right? 20 times 8 times cos 30. Well, 20 times 8 times cos 30 is 138.56 newtons. Sorry, not newtons, joules. Okay, 138.56 joules. That's it. So I said it was similar to last unit. It's not actually that similar. It's much easier. We're not finding the constant force that's pulling it down. because it doesn't actually give us the angle of the ramp, so nothing we could possibly do with that. Okay, now torque. Torque is new, probably. I'm going to treat it as though you know nothing about torque. Torque is the idea that when you are applying force to a rotating object, the force changes, the effect of that force, rather, changes depending on where you apply it. Now, you can demonstrate this yourself very easily. So listen to my instructions, then pause the video and try this. Go to the nearest door, right, and open it using the handle. Probably that's pretty easy. Okay, then try to close it again by pushing very close to the hinge. Okay, so push really close to the hinge. So in my picture here, my wrench, right? If I'm opening the door with a handle, that would be like putting a force right here at the outside of the door, because remember, it rotates over here at the hinge, right? But when I try to close the door by pushing near the hinge, the same door that weighs the same amount is much, much harder to move, right? And this is also true of the idea of just pick up something relatively heavy and hold it close to your body versus holding it with your arm outstretched. You'll find that it is very difficult to carry weight with your arm way out to the side, even though it's the same weight. I mean, why would it be harder to carry in one capacity than another? So the idea with torque, and we have all kinds of tools that take advantage of this, is that the torque, okay, which is the force that in this event is driving the screw into the page, will be given by the length of the radius of whatever's turning times the magnitude of the force that you're using times the sine of the angle between those two things. So there's a couple of things to take from this. F is the force that you're applying. R is the radius vector from the center of rotation. So notice, R cross F is the torque. The bigger the radius, the more force, the higher the torque. So this is why if you apply a lot of force to the door, it makes it easier to open. If you push the door from far away from its center of rotation, it moves much more easily. If you try to open the same door really close to the hinge, you'll find it's far more difficult. You have to use tons of force to get it to move, right? You'll also find that the angle you're pushing at changes as well. If you push perpendicular to the radius, that's the most effective way to move a wrench or to open a door. If you push along the direction of the radius, you're not going to rotate the object at all. Okay, now notice one last thing. Torque is perpendicular to both of these vectors. The screw in this picture either goes into the page if you're tightening it, or comes out of the page if you're loosening it. Okay, so the torque vector itself is a cross product. It's perpendicular to both the rotation and the force. And again, just think about this. Think about this wrench. The wrench is moving, left and right. The force is moving forward and backward, but the screw is moving down, right? The screw is moving in a different dimension than the radius or the force are. Again, torque is a lot like work. It's measured in Newton meters. So let's look at this picture. A bolt is tightened by applying a 65 Newton force to the end of a 0.15 meter long wrench, as shown in the diagram. Find the torque on the bolt. All right. So again, the torque is easy enough. Torque is this number. So tau. Now, unlike work, torque is a I'll just write this one. Torque, tau. That symbol. Okay, so torque is equal to the force, so F vec, and then crossed with the R vec. Okay, so you cross the force vector with the radius vector. Now we know that the magnitude of the torque, so magnitude tau, is equal to the magnitude of F. So just from our, this is a formula from our cross product A. Force times radius times sine of the angle, right? That was our formula there. So we just get 65 times 0.15 times sine of 70. And as an answer, I mean, what is that? 65. $9.16. Now, it's not joules, okay? You don't have the option to say joules with torque, so you just say Newton meters. Now, torque is a vector, which means this answer is not complete. A vector needs a direction. Use the right-hand rule to find out which direction the torque vector points. Find out in which direction the torque vector points. Now, if you are familiar with using a wrench, then you would know that what's happening in this picture is that you are rotating it clockwise, and that tightens. That tightens. If you forget that, then you line the vectors up, right? So here's the force vector, here's the radius vector drawn again, just so that they originate from the same point, right? And you curl force towards radius, and you'll notice that your thumb points, well, I have this wrong, so let me think this through. Did I say that? Oh, sorry, I did. I put force first. You're supposed to put radius first. I'm sorry. So what I wrote here is wrong. I'm glad I did that. Doesn't matter in the work done, but it matters when you're doing the cross product. So there's a common error that hopefully you don't make. Okay, radius comes first. So if you put your fingers along the radius here and curl towards the force, your thumb points into the page, and that tells you the torque is it's tightening. So in this case, the radius vector crossed with the force points into the page. Therefore, the bolt is being tightened. Again, if you prefer, you can just look at the picture and tell me if it's being tightened based on what you know, but you should know how to use that right-hand rule. You will need it for certain questions. So to give our final answer, we say 9.6. So let's say, therefore, the final answer is, okay, so the torque vector equals 9.16 Newton meters into the page. And you can just say into the page or out of the page. Or you can also say tightened or loosened is also fine. I'll understand any of those. Okay, so there will be a couple questions on torque to some on the assignment. Just try them. It is a bit confusing. You may want, if you want to have a wrench or screwdriver or just something to remind you how this works, like even a jar, right? Like just a jar of something that you can open and close. That will work. All may help you with this. Okay, here is where we start to get into the brilliant stuff. Okay, the area of a parallelogram. Now, the area of a parallelogram, we said before, is uv sine theta, because v sine theta would be the height of the parallelogram, and the area of a parallelogram is just base times height. Okay, so that's fine. The area of a parallelogram I don't think you should find as very difficult. The area of a parallelogram with sides defined by these vectors. Okay, very, very simple. The area equals the magnitude of the cross product. So the magnitude of A cross B. Remember that magnitude of A cross B is UV sine, or AB sine theta, and AB sine theta is equal to the area of the parallelogram. So all of these things are the same. The area of the parallelogram is the magnitude of the cross product, so let's do the cross product. A cross B. I start with -1, then 0, then 2, then -1 again. Underneath, I do the components for B. I start with 5, then 8, then 3, then 5 again. Okay? To cross them, I make a series of x's. -1 times 8, take away 0 times 5. So I get -8. I go to the next one. 0 times 3 is 0. Take away 2 times 8 is -16. And I go to the last one. 2 times 5 is 10. Take away -3 is +13. Now again, whenever you do the cross product, my advice would be, let's just take a second to make sure we did it right. Okay? Because again, like, you don't want to do a whole question and then come back and realize your cross product was off. So let's just quickly do the cross product here. So 2, -1, 0 is sorry. Yikes. Okay, sorry. It's so hard to fit all on one page. A is 2, -1, 0. B is 3, 5, 8. Okay, and those are our two vectors. Now again, I'm going to cross A with B, and I get the answer I got. Remember, if you want to check it, you can check it even faster by going dot product of U with A, which should give you 0, dot product of U with B, which should also give you 0. So again, you could check this pretty simply in your head. -8 times 2 is -16. -16 times -1 is +16, and 13 times 0 is 0. So they all add up to 0. This one's a little bit trickier, but try and think of it as I have 3 -8s, and then I have 5 -16s, so that's -104. And then I have 8 +13s, which is also 104, and it adds up to 0. Anyway, so I know I did this right. Now, the area is simply equal to the magnitude of this vector. So the magnitude of this vector would be the square root of 64 plus 256 plus 169, right? Which is just simply those three numbers squared. So the first two add up to 320. The second one would be 320 plus 169 would be 489. And I don't know that one off the top of my head. It might be 23. Nope, 22.11. So the area of the parallelogram would be 22.11 units. Now, let's just quickly show how you could, another way to do this question to check your work. Okay, here are my two vectors, right? U and V. Now, let's make some points. So O plus A, O plus B. Sorry, yeah, the U vector's messing me up here. We don't actually need that. Okay, so here are my two vectors. Okay, now if I wanted to complete a parallelogram here, I go O plus A plus B. How does it get there? It goes along A and then it goes along B to make a parallelogram, right? Now if I go polygon OACB, it draws that parallelogram and it has an area of 22.11, right? Exactly like what we said it should have. So that's another way you can do that. Okay. Find the area of the triangle with vertices A, B, and C. And then we're going to do this parallelepiped, and then this will be done. Yeah, okay. All right, find the area of a triangle with vertices A, B, C. All right, now, to find the area of a triangle, you could find the base, find the height, which you would have to do by projecting, or you could do something really clever. Now, what we're going to do is something really clever. Let's draw it first, and then you can see what I'm talking about. So A is 1, 1, 1. B is -2, 0, -4. C is 4, 3, 2. Okay, now, I'm going to draw three vectors here. So AC equals vector AC, AB equals vector AB, and CB equals vector CB. Now to get the area of this triangle, right, what are some things we could do? Well, one thing we could do is we could project, right? If we projected, I'm just trying to think what you would want to do here to get the... I don't want to do the projection. I'm just trying to think of how it could work, but... Yeah, I think if you projected BA onto AC, you could get like a little, you could get this value right here, and that might help you get like a big right triangle, and then you could subtract the two. It would work. It's nice. I'd love to see somebody do that. So let me just to clarify what I meant. I don't think this actually has a project command. First time GeoGebra's let us down, eh? So if we take, how do you do a projection again? So we do AB, so we dot AB. I want to project AB onto AC, and then divide it by the length of AC. And I think if we do that times AC divided by, so we just multiply it by a unit vector. I think that tells us, yeah, I think that's right. So we go A. Sorry. Okay, so you see what I've done? I projected AB, I projected this onto AC, and it gave me the missing length I needed over here that I could now use to do a right triangle. Because if I do vector DB, then I know that the vector, and then I do AC dot AC and W, it should be 0 because it's perpendicular, and now I have a right triangle, and I could use this to figure it out. Okay? Now, that's good. It's a good way of doing it. If you understand what I just said and you want to give that a try, please post it and show us how to do it. It's an excellent solution. It's not the solution I'm going to teach you though. Okay? I know it's a long time for a tangent when I'm already an hour and 2 minutes into something, but you just have to forgive me for being enthusiastic. Let's think about this triangle a different way. Okay? Let's think about this triangle as half a parallelogram, right? So what if we were to say if we start at point A and then add vector AC and add vector AB, what is this fourth point over here, D? This D, right, is the fourth point of a parallelogram that is exactly double, right, the area of our triangle, because our triangle is half of this parallelogram, right? There's a top triangle and a bottom triangle. So a really clever way to approach this question is to do it this way. Consider vectors AB and AC so that you have a point D, which is point A plus AC plus AD, i.e. it's the parallelogram. Parallelogram by adding the two vectors and their origin point. Okay, you have a point D. Then find the area of this parallelogram and divide it by 2. Okay, so what I'm going to do here is I'm going to do vector AB, magnitude of AB crossed with AC, and I'm going to divide it by 2. And that's it. And this is the area, any triangle, the area of any triangle can be done just by doing this, right? This is where, as like I said, this is where you start to get into the really brilliant stuff in this unit, like how some of these formulas can work together to solve problems and accomplish things, right? So let's find vector AB. Vector AB is always just destination minus origin. So vector AB for us is going to be, if you start at vector B and subtract your way back to vector A, you would find that vector, okay, so, yikes. Okay, so we had to get to -2 from 1, so -3. 0 minus 1 is -1, and -4 minus 1 is -5. So that vector would get you from A to B. Then we need vector from A to C. And vector AC would be, to get from 1 to 4 is 3, to get from 1 to 3 is 2, to get from 1 to 2 is 1. Okay, so that's that. Then we're going to cross product these vectors. So -1, -5, -3, -1 again. 2, 1, 3, 2 again. Okay, so we'll go ahead and cross product them. And we get, let's just get this formula here, is equal to, okay, let's cross product. -1 times 1 is -1. Take away -10 is +9. Next one, -15. Take away -3 is -12. Final one, -6. Take away -3 is -3. Okay, again, as always, it's worth to just check this. Let's go cross AB, AC. And we get 9, -12, -3, which is what I said it should be. We'll take the magnitude of this. So magnitude, the cross product, is just equal to the square root of, let's see, 81 plus 144 plus 9, which is square root of 234. And we divide it by 2. And that's going to be the area. Equals the area of the triangle. Now, let's check that. So length U, E squared should give us the 234, right? That's what we said, yes. And then we said this magnitude, E, sorry, yeah, right, I'm looking at this thinking, how come it's double? Then we go E divided by 2. So I'm saying the area of the triangle is 7.65, which is consistent with the idea. So let's hide this thing now. And let's draw a polygon, A, B, C. 7.65 is its area, right? That's what GeoGebra measures its area to be. 7.648853, which is exactly what we said. Okay, brilliant. I was just so impressed with that solution when I saw it the first time, right? So area of a triangle, you did this question earlier in the unit when it was a right triangle and it wasn't so hard. This is not a right triangle though. You could find its magnitude. Sorry, I did want to say there is another good solution to this, right? Let me do one more solution to this triangle that you could do. Okay, forget making it a parallelogram for a sec. This triangle, you know all three of its lengths because one of them is this vector, one of them is this vector, one of them is that vector. You could just solve those three lengths. And then you could use your dot product to get the angle between them and start getting the angles in the corners, right? Then you know everything about it and you could sort of split this in half, get a height, and figure out. However, I think you'll agree that in the long run, this cross product solution is really nice. Like, it's just an excellent way of dealing with triangles. It takes what might be a 15-minute question and makes it a 5-minute question, which is superb. Okay, final concept for today is what's called a parallelepiped, which is a three-dimensional parallelogram where you have three vectors originating and then every other vector is parallel to those three. Right? So like A is over here, A is over here, A is over here, A is over here, B, 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 and then C, 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 right? The volume of the parallelepiped is equal to the volume of the, the area of the parallelogram. So you get the area of this parallelogram here. And then, right, you multiply it by the height of the object. The height of the object is you project, right, the other vector onto the normal. So the normal, when I say normal, I mean a number that I need something that's perpendicular to both. So it's difficult for me to kind of explain this in this format, but maybe with a piece of paper you could try it, or I can try like designing a GeoGebra that might help us understand this. But if the height of your parallelepiped is you project A onto B cross C. And B cross C would be, we know that the height of this parallelepiped would be coming straight up. And so would the cross product, right? The cross product of B and C would point straight upward. If we project A onto that normal, it tells us the height of the box, and then you just multiply the base times the height. Okay? I don't think I would worry too much about that explanation, so much as just to look down here at the way that it all kind of cancels out. It cancels out into the triple scalar product. And the triple scalar product is simply a vector dotted with the other two vectors crossed. You cross first and then dot at the end. Okay? So how do you get the volume of a parallelepiped? Don't worry too much about visualizing it and explaining it and all that stuff. I just remember the formula is fine, right? The idea of projecting onto the normal is something we'll come back to next unit anyway. I don't think it's a huge priority for right now, but it is an interesting thing to try to think about in anticipation of what we're doing next unit. Okay, so you would cross any two vectors you want, and then you would dot that with the third vector, and that would tell you the volume of this shape. Okay, so I'm gonna stop it there. You've got a lot to work on and review, and feel free to reach out if you need any help with anything. And best of luck.